Interference in wedge-shaped film. In the last two lectures, we studied interference in thin film of uniform thickness. That is, we studied interference in thin parallel film whose thickness remained constant. But in this lecture, we are considering wedge-shaped film. Thickness of this wedge-shaped film is not constant. Thickness changes. So let's first draw the diagram. Let's say this is a plane surface GH and there is another plane surface GH dash or GH prime. So this GH and GH prime, these are two plane surfaces which are inclined to each other at an angle, let's say alpha. This angle over here is alpha, and this alpha is called wedge angle. So very thin film between these two plane surfaces GH and GS dash is enclosed, and as you can see in this case, thickness of the film is increases in this direction. As you go towards this direction, its thickness increases. But the thickness will remain constant parallel to the wedge. This is wedge over here. And this GH and GH dash are not just lines, they are plane surfaces. So, parallel to the wedge, thickness remains constant, but from point G to H, thickness increases. Thickness of film, which is enclosed between these two surfaces, enclosed between two surfaces, GH and GH dash, is variable. Thickness is not constant. That is, thickness increases from G to H and thickness remain constant parallel to H. So parallel to this wedge, this is the wedge over here, the thickness remain constant. But perpendicular to the wedge, thickness increases. Then let's say I am showing incident ray. This is the incident ray AB. So in this case, AB is incident ray of wavelength lambda. So in this case, at point A, at point B over here in this diagram, it is partially reflected and partially transmitted. So before I show, I, before I, sh- I am show, I am not showing this reflected ray, but before that, let me show the normal drawn from point B to the surface GH dash. So this is the normal. What I am drawing is normal to the above surface GH dash. Let me redraw it again. So this is the normal to the above surface. Now at point B, what happens? The ray is partially reflected and partially transmitted. Let's say the ray is reflected along BR. BR is the reflected ray and it is partially transmitted. Let's say it is transmitted along the direction. Let me verify it. So this ray is partially transmitted along BC. Let's say this point is C over here. Along point BC, the ray is partially transmitted. Then at point C, again there would be partial reflection and refraction. We are interested only in the reflected light. So let me first show this is the normal to the lower surface. Normal to the surface GH drawn from point C. Okay, at point C again there would be partial reflection and partial transmission. We are not interested in transmitted ray. So I am going to show only the reflected ray. Let me verify it first. So it is partially reflected along, say, CD. Along CD, it is partially reflected. This is reflected ray from point C and this is my point D. Then at point D, again there would be partial reflection and refraction. We are not interested in the reflection here. What we want is the transmitted ray. So from point B, this ray comes out. Along, say, DR1. So in this diagram, this BR and DR1, BR and DR1 are reflected rays derived from, these rays are derived from incident ray AB. Hence, they are coherent. See, there is a single incident ray in this case AB. From this single incident ray AB, we got two reflected rays BR and DR1, and hence these two rays are coherent. These two rays interfere. This BR and DR1 are not parallel. BR and DR1, they are not parallel to each other. They interfere and produce the interference pattern. What we have to find is the path difference between the rays BR and DR1. Find path difference between BR and DR1. To find the path difference, we have to make some arrangement over here. What we are going to do is from point D, I am going to draw normal on this ray BR, and let's say that point is F. Similarly, I am drawing the normal from point D on this BC, and that point is E. This point is E. So what I have done is DF and DE normals on the ray BR and BC. DF and DE are normals on BR and BC on rays BR and BC respectively. Let's see the diagram. Normal means this is 90 degree. One more arrangement I would like to do over here is I am going to extend. First, I am going to draw normal to the lower surface from point D. Okay, this is a normal at point D to the lower surface. And I am gonna expand this BC in the forward direction. This BC I am extending to the forward direction so that it meets at this normal at point P. Let's say this is point Q. Thickness of the film at point D is, let's say, T. T is the thickness of the point at thickness of the film at point D. So what we are assuming here, thickness of the film at point D is equals to T. The T is changing everywhere, but at point D, let's assume that its thickness is T. So in the diagram, this DQ is equals to T. The dq is equals to T. Now let's verify the angles. Now this is angle of incidence here. This is angle of refraction. Wedge angle is alpha. So this angle, which is angle between the normals to the upper surface and lower surface, this is also alpha. But these angles, these two angles are r plus alpha. This angle is also r plus alpha, and therefore this angle is also equals to r plus alpha. Now this angle over here is r, so this one is 90 minus r, this is 90 over here, and so this angle here is equals to r. Similarly, in this case, this angle is I, this angle is 90 minus I, this one is 90 here, and so this angle is equals to I. So these are the angles. So what we have to find is the path difference between the ray BR and DR1. So first write geometrical path difference. Geometrical path difference between rays BR and DR1 is equals to BC plus CD minus BF. So let's see the diagram. See our action starts at the point B. At point B, the ray is reflected along BR. By the time this ray reaches at point F, this refracted ray travels along BC and then CD. So, when that ray reaches at point D, the reflected ray reaches at point F. So, the path difference between these two rays is this BC plus CD minus BF. That is geometrical path difference. Then we have to find optical path difference. Let's say mu is the refractive index of the film which is enclosed between these two plane surfaces GH and GS dash. Okay, between these two surfaces refractive index is mu. So this path BC plus CD is in the medium whose refractive index is mu, while this path BF is in the air, and hence geometrical path difference is given here BC plus CD minus BF, and therefore optical path difference, which is denoted by letter delta, is equals to mu times BC plus CD minus BF, and this is our equation 1, optical path difference. Then we are going to consider triangles. Two triangles we are going to consider here. The first one is BDF, and second one is BDE. Consider triangles BDF and BDE. In this triangle, angle D is equals to I, and in this triangle, angle D is equals to R. Then according to Snell's law, mu is equals to sine I upon sine R. Let's see how much is sine I in this triangle and sine R in this triangle. So in the first triangle, this is I, and sine I, in this case, sine I is equals to Bf upon Bd. Bf upon Bd is sine I, and sine R in this triangle, sine R is equals to this Be upon Bd. So let us write that. So in this case, sin I is Bf upon Bd, and sin R is equals to Be upon Bd. So this Bd cancels with this, and we get Bf is equals to mu times Be, and this is our equation 2. Then substitute equation 2 in 1. In equation 1. Then optical path difference delta is equals to this BC plus CD. But I will replace this BC. See in the diagram, BC. This BC I can write BE plus EC. Okay, BE plus EC I can write. So this BC is equals to BE plus EC. I will write that as mu times BE plus EC. Then this CD as it is, plus CD. Then minus BF, but this BF is mu times BE. So mu is common, so in the bracket minus BE. So this BE cancels with this BE. What I get is delta is equals to mu into EC plus CD. But this mu equals to EC plus CP, since CD is equals to CP. This value of CD is equals to CP, as you can see in the diagram. This CD is equals to CP. This is equals to this, that is dq equals to qp. So this is also equals to t, and the angle is r plus alpha. This is also r plus alpha. So CD equals to CP as per the diagram. And then this EC plus CP, EC plus CP, I can write as a EP. EC plus CP is EP. See the diagram. Let me highlight it. This is my E, this is C over here, and this is P. So EC plus CP equals to EP. Directly I can write EP. And this is my equation 3. Then I am going to consider triangle DPE, where angle P is equals to R plus alpha. Let's see that in the diagram. I am considering the triangle. This is my D over here. This is point P over here. And this is point E over here. So I am considering the triangle DPE. And angle P over here is nothing but R plus alpha. Then what would be cos R plus alpha? Cos R plus alpha is equals to EP upon PD. From this, cos R plus alpha is equals to this point P, this point P, this point E. So EP upon PD, EP upon PD, where PD is equals to this T and this T, 2T. So let's go to the equation. Cos of R plus alpha is equals to EP upon PD, and this PD is equals to 2T. So EP upon 2T, or EP is equals to 2T cos R, and this is equation 4. I will substitute equation 4 in equation 3. Equation 4 in equation 3. Then I get optical path difference delta, this is delta, is equals to mu times this. So twice mu t cos of R plus alpha. So this is the path difference. But we have to correct the path difference. So there is a correction. What is the correction? Correction is if light is reflected from denser medium, its phase changes by pi, or path changes by lambda by 2. You know this condition. So in this we have to make the correction. First we have to check from the diagram that we know that the two rays BR and DR1 and BR, these two rays interfere. We have to check if there is any ray is reflected from denser medium. Now here, this is air, this is the film here, and here is the air. So as you can clearly see that at point D, at point this B, this BR is reflected from the film, boundary of the film. And so that is a reflection from denser medium. While for the ray dr1, we got this dr1 by first refraction or transmission at point B, then it is reflected at point C, and then it comes out from point D. So it is transmitted to point D. So for this ray, there is only one reflection which is at point C. But that reflection is from the air. Here is the air. So that is the reflection from rarer medium. So only one ray out of this Dr and Dr1, Dr is reflected from the denser medium. So the path will change by lambda by 2. So in this equation, this delta is equals to twice mu t cos of r plus alpha. We have to subtract lambda by 2. And this is a final path difference. Now let's see the condition for constructive and destructive interference. Constructive interference. For constructive interference, this path difference 2 mu t cos of r plus alpha minus lambda by 2 should be equals to n lambda. Let us simplify this because here is also lambda, here is also lambda. So we will simplify this as 2 mu t cos of r plus alpha is equals to n lambda plus lambda by 2, and that is equals to 2n plus 1 lambda by 2, which is 2 mu t cos of r plus alpha. So this is the condition for constructive interference. When 2 mu t cos r plus alpha is equals to odd multiple of lambda by 2, you get bright fringe in the reflected light of the wedge-shaped film. Then let's find the condition for destructive interference. For destructive interference, this 2 mu t cos of r plus alpha minus lambda by 2 is the path difference, and this should be equals to 2n plus 1 lambda by 2. Simplify this by shifting this lambda by 2 to the other side. We get 2 mu t cos of r plus alpha is equals to 2n plus 1 lambda by 2 plus lambda by 2. Simplify it, you get 1 plus 1 lambda, which is 2 mu t cos of r plus alpha. But if n is integer, then n plus 1 is also integer. So instead of writing n plus 1 lambda, you can directly write n lambda. 2 mu t cos of r plus alpha is equals to n lambda. And this is the condition for destructive interference in the reflected light from the wedge-shaped film. So we got here condition for constructive and destructive interference. Now in the lab, what happens, there is a normal incidence. Light fall normally on the film. This is the film here. I have shown some angle I in this case. But what will happen if this I equals to 0? That is when light fall on it normally. So we will consider the case of normal incidence. For normal incidence. For normal incidence, I equals to 0, angle of refraction is also 0. Then path difference would be 2 mu t cos of alpha. R is 0 in this case. So I am not writing r plus alpha, r is 0, minus lambda by 2 is the path difference for normal incidence. As you can see in this equation, this mu is constant, alpha is constant, lambda is also constant. The only variable is the thickness. So in this case, the thickness is variable along direction GH, G to H, but it is constant parallel to the edge. As I said earlier, the thickness remains constant parallel to the edge, but variable along the film length. So only variable is T. So path difference in this case is introduced by varying thickness. Path difference is introduced by varying the thickness. And that's why you get the straight dark and bright fringes. What you get is, because of this, you get straight, dark and bright fringes obtained parallel to the edge. Because parallel to the edge, thickness remains constant. Let's see the diagram. In this diagram, this is the edge over here. Parallel to this edge, thickness remains constant, but in this direction, thickness changes. So parallel to the edge, you get alternate dark and bright fringes. And these fringes have equal width. The fringes have equal width, or thickness of the fringe is constant. Okay. For these fringes, they have equal width, or you can say that the fringes have constant thickness. And such a fringes are called Fizeau fringes. Okay, Fizeau fringes are fringes of constant thickness. Now, what we consider is the condition of normal incidence. When we are considering the normal incidence, then what would be condition for constructive and destructive interference? The path difference is how much? 2 mu t cos alpha minus lambda by 2. When this is equals to n lambda, we get bright fringe. That is when 2 mu t cos alpha is equals to 2n plus 1 lambda by 2. We get bright fringe. And when this 2 mu t cos alpha, minus lambda by 2 is equals to 2n plus 1 lambda by 2, you get the dark fringe. And after simplification, what we get is 2 mu t cos alpha is equals to n plus 1 lambda, or that is equals to n lambda. That is when n is integer, n plus 1 is also integer. So instead of writing n plus 1, we can write n lambda. So when this 2 mu t cos alpha is equals to n lambda, this is for dark fringe. So we got the two conditions here. Condition for bright fringe and condition for dark fringe. Using this, Let us find fringe width. We are going to find fringe width. For that, let me redraw that diagram of wedge-shaped film. This is the wedge-shaped film over here. The angle is alpha. And let's assume that I am getting nth bright fringe obtained at distance xn at thickness t. So let's say that at this point, thickness of the film is t. Here the thickness is t. And the length of the film is xn. So at distance xn from this point, I am getting nth bright fringe. At this point, I am assuming that I am getting nth bright fringe. Then what would be the equation? So let us take tan alpha in this case. What would be tan alpha? Tan alpha would be t upon xn is equals to t upon xn, or t is equals to xn tan alpha. But I have the condition for bright fringe. Condition for bright fringe is 2 mu t cos alpha is equals to odd multiple of lambda by 2. This is the condition for the bright fringe. So in this equation, I will replace this t with xn tan alpha and rewrite the equation. So 2 mu, this t is equals to xn tan alpha into cos alpha, and that is equals to 2n plus 1 lambda by 2, or 2 mu xn sin alpha is equals to 2n plus 1 lambda by 2, and let's say this is my equation number 5. So this is for nth bright fringe. Then I will take for n plus 1th bright fringe. Here in this case, let's say that at a distance xn plus 1, where the thickness is say t dash, t prime, and the distance is xn plus 1. At this distance, I am getting n plus 1th bright fringe. At distance xn plus 1, I am getting n plus 1 bright fringe. Then this equation 5 will become for nth bright fringe is 2 mu xn plus 1 sin alpha, and this is n equals to n plus 1. So I get 2n plus 3 into lambda upon 2. And this is my equation 6. What I have to find is fringe width. I know the equation for nth bright fringe and n plus 1th bright fringe. So fringe width would be equation 6. To find fringe width, I have to subtract equation 5 from equation 6. So equation 6 minus equation 5. That would be 2 mu xn plus 1 minus xn into sine alpha, that is equals to lambda. So I'm just doing 6 minus equation 5. Let's take this xn plus 1 minus xn is equals to beta, which is fringe width. Then I get 2 mu beta sine alpha is equals to lambda, or what I have to find is a fringe width beta. So beta is equals to lambda upon 2 mu sine alpha. 2 mu sine alpha. And if alpha is small, if alpha is very small, then sine alpha is approximately equals to alpha. And so the fringe width beta is equals to lambda upon 2 mu alpha. So in this see, lambda, mu and alpha constant. All the factors to the right hand side are constant, hence beta is equals to constant. So we get fringes of constant thickness in this case. Now let us find how to find thickness of the wire using this wedge-shaped film. Thickness of wire or any thin film, you can find its thickness. What we have to do is we have to enclose that wire between two glass plates. So this is one glass plate. At this point, let us keep the wire whose diameter is say D, and on top of that let us keep another glass plate. So what we have here is wire whose diameter is D. This is alpha, and in this case let us assume that length of the film is L. Then we can write tan alpha is equals to D by L, or we can write alpha is equals to D by L if alpha is very small. If alpha is very small, then this tan alpha is equals to alpha. But we have, the fringe width is given by this letter B, beta, which is equals to lambda upon 2 mu alpha. This equation for the beta. And in this case, let us replace replace this alpha with d by L. So what we get is beta is equals to d, sorry, we will get beta is equals to lambda upon 2 mu. This alpha is equals to d by L. So we get beta equals to this lambda L upon 2 mu d, or d, which is diameter of the wire, which is equals to lambda L upon 2 mu beta. Mu is equals to 1 for air, and therefore the d is equals to lambda L upon 2 beta. So using this equation, you can find diameter of the given wire, or instead of wire, you can enclose here, very thin film, whose thickness also you can find using this equation.